The main focus of this week's topic is understanding probability. It is one of the most asked questions in data analysis. Not only do people want to know what has happened thus far with their information, they want to know what might happen in the future. Insurance companies want to know if all age groups are likely to have the same number of accidents. Medical researchers look at things like age, gender, lifestyle, and family history to estimate the probability of a person getting a particular disease. Engineers want to know the probability that a machine can make a certain number of widgets before it breaks down. As you can see, probability is widely used in many fields and can be useful in many ways in data analysis. Probability is the likelihood that something is going to occur. It looks at past trials and their outcomes and try and determine if a certain event happens, can we predict the most probable outcome. The challenge is that in cases where there are multiple outcomes, all of the outcomes are not equally likely. In this section, we're going to cover some of the basic rules for understanding probability. We'll talk about trials and outcomes, how to decide if something is independent or disjoint, and when you might need to add or multiply probabilities together to get the answers to your questions. A trial is considered to be an observation of something random occurring. The results of the observation is considered an outcome. If you think of all possible outcomes for a given trial, that would be your sample space. Grouping particular outcomes together to help answer a question is considered an event. Let's say you reach into your wallet and pull out a random bill. Pulling out the bill is a trial, and which bill you pull out is an outcome. In this case, the sample space is all the possible bills you could pull out of your wallet. For this explanation, we'll limit ourselves to only U.S. bills in circulation. If we're interested in certain types of events, we can combine outcomes in different ways. For example, the event A is equal to a bill that does not have a precedent on it is how we describe a collection of outcomes. The event C, which we'll define as enough money to pay for a $14 meal with one bill, is a set of outcomes containing the dollar bills 20, 50, and 100. One thing to note is that for most people, the outcome of pulling out a $1 bill is generally much more likely than pulling out a $100 bill. Without knowing the probability of how many of each type of bill you'll usually expect to carry, we can't calculate the likelihood of you pulling out a $1 bill over a $100 bill more often. Another way to think of it is that even if you buy a lottery ticket, your chance of winning is not 1 in 2, win or lose. Another important set of terms to know when thinking about probability are independent and disjoint. We use these terms when talking about outcomes and events, and this allows us to find probabilities of multiple outcomes. An independent event means that the outcomes from one trial don't have any effect on the outcomes of any of the other trials. A disjoint event means that each outcome is mutually exclusive and have no outcomes in common. Independent events may have outcomes in common, even if there are separate trials. So, how do we figure out what our chances of a particular event occurring? First, we need to decide whether or not we think our outcomes are equally likely or not. Theoretically, if a deck of cards is well shuffled, the chance of any of the 52 cards being on top of the pile will be the same. And if a die is thrown in a game of Yahtzee, it should have an equal chance of landing on any of its faces, as long as it's not a weighted dice. If you know that the outcomes of a trial have an equal chance of occurring, it is fairly easy to calculate the probability. The probability that you choose the Queen of Hearts off the top of a deck of cards is then 1 chance in 52. Rolling a 4 on your dice throw is 1 chance in 6. If you want to know the probability of more events with equally likely outcomes, you can just count all the outcomes in the event and divide by the total possible outcomes. For example, if we want to know the probability of drawing an ace from a deck of cards, we can count the number of aces in a deck, which is 4, and divide that by the 52 cards possible. This gives us a 1 in 13 chance that an ace will be drawn. If your possible outcomes are not equally likely, then you'll need to use a different set of rules that we'll talk about in a few minutes. Another thing to think about is whether or not a particular event can actually occur. If the answer is no, the event can occur, the probability will be 0. If the answer is yes, the event always occurs, the probability will be 1. If you think that an event may occur, then you have a probability between 0 and 1, and you'll have to do some calculating to figure out exactly what it is. A probability must always be between 0 and 1 and can never be negative. Also, if you have more than one outcome that you are looking at, the probabilities of all the outcomes must add up to 1. This means some outcome of some sort will happen all the time. This makes it easy when we already know the probability of some particular outcome occurring, and we want to know the probability that it is not going to occur. For example, if you know that the stoplight on Main and Division Street is green 35% of the time you drive up to it, you might also want to know the probability is that the light won't be green when you get to that intersection. Since you know all possible outcomes have to have probabilities to add up to 1, you can subtract the fact that the light is green 35% of the time from 1 to get the answer. So 1 minus 0.35 equals 0.65, or 65% of the time the light will not be green for you. This is called the complement rule. If you have events that are disjoint, meaning they have no outcomes in common, you can find the probability of multiple events occurring by adding their probabilities together. Let's go back to our example of the stoplight at Main and Division Street. The event is disjoint because the light cannot be more than one color at the same time. You know from keeping track over multiple days that the light is green 35% of the time you approach the intersection. After looking back at your data, you discover that the light is yellow about 4% of the time. What your neighbor wants to know is, what is the probability that the light is red when you get to the intersection? Because these events are disjoint, you can use the addition rule. So the probability that the light is either green or yellow when you get to that intersection is 0.35 plus 0.04, or 0.39. Now that you know the probability that the light will be green or yellow either 39% of the time, this still doesn't answer your question about the red light. Since you know the probabilities must add up to 1, and the only other option for the light is red, you can use the complements rule to find the probability of the light being red. This would mean that you would have 1 minus 0.39, or 0.61. Therefore, 61% of the time, the light is red. Now, let's take a look at how you would handle probabilities for independent events, or events whose outcomes have no influence on each other. Your neighbor is very interested in how you figured out the probability that the stoplight will be red at Main and Division Streets, and wants to know what else you can figure out. He wants to know if you can tell him the probability of the light being red on both Monday and Tuesday. The color of the light when you get to the intersection each day does not depend on the color of the light that you saw the day before, even though sometimes it sure seems like it does. This makes the events independent. When events are independent from one another, you cannot add their probabilities together. You need to multiply them. I know this seems counterintuitive, but that's just the way the rule works. Back to your neighbor's question. You know the probability of the stoplight being red on any given day when you get to the intersection is 61%, and it will be the same regardless of the day of the week. In order to find the probability that you will encounter a red light on both Monday and Tuesday, you need to multiply the probability of the light being red on Monday with the probability of the light being red on Tuesday. This gives you 0.61 times 0.61, or 0.3721. You can tell your curious neighbor that the probability of encountering a red light 2 days in a row is only 37%. Let's go back to the example of pulling random bills out of your wallet. If you randomly take a bill out of your wallet, you can look at it to see a few different things. First, you can see what the denomination of the bill is. And secondly, you can see if there's a picture of a building on the back of the bill. In the U.S., there are pictures of buildings on the back of all but 2 bills, the $1 and $2 bills. What is the probability that a bill that you have randomly taken out of your wallet is a bill with a building on the back, A, or a bill that is an odd-numbered value, event B? The or in the question should be a big flag to you that you need to use addition to figure out the probability. However, in this case, the 2 events, A and B, are not disjoint. The $5 bill is in both sets. This means that we cannot just add up the probabilities. The best way to handle this type of situation is to draw a picture known as a Venn diagram. If we draw a picture on both events and place the bills in each set, you can see that the 2 events overlap with the $5 bill. This is called the intersection of A and B. In order to get a true answer to our questions, we need to subtract out the probability of the intersection of A and B. This is so that we don't count the $5 bill twice. If you look at the diagram again, you can see that the $2 bill doesn't meet any of our criteria for events A and B. So it sits just outside the diagram. This gives us the equation P of the probability of odd number value or building is equal to the probability of obtaining an odd number plus the probability of obtaining a bill with a building on it minus the probability of a bill containing both an odd number and a building. If we look at the equation in a general fashion, we could see that the probability of A or B is equal to the probability of event A plus the probability of event B minus the combined probability of event A and B. Sometimes we want to know the probability of something occurring based on whether or not something else has already happened. Oftentimes this can happen when we have a number of different categories and we need to know one or two things about each. This is where conditional probability comes in. Conditional probability gives you the probability of something happening given that a particular characteristic is present. It is used to answer questions like, of the doctors at the clinic, how many have an undergraduate degree from the University of Nebraska? The easy answer is, it depends. The next part of the conversation usually centers around what it depends on. If we want to find the probability that doctors at the clinic have a degree from the University of Nebraska, we need to use conditional probability. Here's an example from psychology. The data came from a survey of children in grades 4 to 6 in the state of Michigan, with roughly a third of the sample coming from a rural setting, 1/3 from a suburban setting, and 1/3 from an urban setting. The children were asked whether or not they had a primary goal of getting good grades, to be popular, or to be good at sports. Their answers are detailed in the table. Even though we don't have any actual probabilities in this table, only counts, we can use this information that it provides to help us determine different probabilities. For example, the probability of a student being a girl would be found by dividing the number of girls, 251, by the total number of students, 478. This equation gives us 0.525. We can also do the same thing when we want to know the probability of intersections, such as what is the probability of choosing a girl who wants to be popular out of all the students. To find this, we look at the table to find that 91 girls answered popular as their primary goal. When we divide this number by the total number of students, we get the probability of being a girl and popular is 19%. Now comes the conditional part. What we want to know is, what is the probability of selecting someone who wants to be good at sports, given that we have already selected a girl? To answer this, we need to restrict ourselves to only looking at the line of the table for girls. And this is our condition. We show the conditional probability by writing P sports given girl, which is equal to 30 divided by 251, or 12%. Notice when we divide by the total, we are only dividing by the total number of girls, not the total number of students. This is because our construction restricted us to only girls. If we did the same calculation for boys, we would divide 60 divided by 227 to get 26.4%. This is more than twice the probability for girls. Using conditional probabilities, you can compare the probabilities of multiple groups and multiple outcomes. In a similar vein to the general addition rule, there is also a general multiplication rule. The big difference between the general rule and the version that we've covered previously is that the general version doesn't need to have independent events. We've already discussed a bit about conditional probability, so we could use that information to generalize our multiplication rule for all types of events. The general multiplication rule says that the probability that event A and event B both occur is the probability that event A occurred multiplied by the probability that event B also occurred. Another way to say this is the probability of event A occurs multiplied by the probability that event B occurs given that event B occurred. Do you see the use of conditional probability here? You can also rearrange things if you want to know about the probability of event B. Sometimes it's easier to think about probabilities by using a picture. A great one to use is a probability table. This allows you to see what it is that you know and what you need to calculate. Often, if you fill in a table, you can answer all kinds of different probability questions with ease. We'll start this scenario by going to a drunk driving example. The annual police report said that 78% of suspects get a breath test, 36% get a blood test, and 22% get both tests. We can start a table to see what it is that we actually know. Here's what the table looks like with the information that we are given. If we use simple addition and subtraction, we can fill in the rest of the table. Here is our table filled in. It is much easier to do that than trying to figure out the probabilities without the use of a table. Now that we have our table filled in, we can use it to answer some questions, even though we did not originally have this much information provided to us. Now that you've learned all about how to calculate probabilities, let's put one more thing into the mix, the influence of replacement. Replacement, or lack thereof, can greatly influence how your probabilities turn out. For example, let's say that there's a big bag of marbles sitting in front of you on a table. The bag contains 10 marbles, 7 of which are black and 3 of which are white. If you draw out one marble from the bag, there's a 3 in 10 chance that you'll draw a white marble. If you put the marble back in the bag, the next time you take a marble out, you're still taking a marble from a total group of 10 marbles. If you take out a marble, it turns out to be white, and you set it on the table next to the bag, the next time you draw a marble from the bag, you're not working with a bag of 10 marbles anymore. You now only have 9 to select from. This means that you now have a 2 in 9 chance of getting a white one on the second draw. If you want to know the chance that you get a white marble on the first try and a white marble on the second try, you can use the general multiplication rule to calculate the probability of this occurring. This equation would be the probability of drawing a marble on the first try, 3 divided by 10, times the probability on the second try, 2 divided by 9, which gives us about a 6.7% chance. You would get the same result even if you try to reverse the order of the draw. We can actually use this information to draw a diagram that can make things a bit easier to see than straight equations. Probably the best type of diagram for the use of understanding probabilities and conditions is a tree diagram. This allows you to see the probabilities rather than just having to look at equations. Walking through an example should help see the benefit of this type of diagram. Let's look at some data that are widely available on binge drinking. For men, binge drinking is defined by having 5 or more drinks in a row. For women, it is defined as 4 or more drinks in a row. According to a study by the Harvard School of Public Health, 44% of college students binge drink, 37% drink moderately, and 19% abstain entirely. Another study from the American Journal of Health Behavior found that among binge drinkers aged 21 to 34, 17% have had an alcohol-related car accident, while only 9% of those in that age group who don't binge drink have had that type of accident. We're going to use this information to construct a tree diagram. With this information, what would the probability be that a randomly chosen college student who binge drinks will also have had an alcohol-related car accident? A tree diagram is useful here because it can help to see the sequence of events. If we start out by putting 3 branches of our tree to define the type of drinkers, we can put the probabilities from the study onto one of the branches. If you add them up, they will equal 1. We are also interested in car accidents to answer our question. According to the second study, having an alcohol-related car accident depends on one's drinking behavior. In order to show that the outcome of having a car accident is conditional upon drinking habits, the next set of branches on the tree would reflect the possible options in each case, either having an accident or not. We draw the set of options on each of the drinking branches as the probability of an accident is conditional. We add in the appropriate probabilities from the second study. These probabilities will also add up to 1 because they cover all possible combinations and outcomes of drinking behavior in car accidents. Now we can answer our question. The probability of a random student being a binge drinker and having an alcohol-related car accident can be determined by our tree. We can look at the branches that represent that outcome and use the general multiplication rule to multiply the probabilities along the tree branches together. So the probability of being a binge drinker and being in an accident is equal to the probability of being a binge drinker times the probability that you've been in an accident given that you're a binge drinker. This gives us 0.44 times 0.17 or 0.075. We can find the probabilities for each of our outcomes. Our tree diagram also lets us see that the final outcomes are disjoint. This means that we can add up the probabilities to get a probability for compound events. For example, if we wanted to know if a random student has had an alcohol-related car accident, we could look at all possible outcomes on the right side of our tree and add up the probabilities for all those in which an accident has happened. This gives us 0.075 plus 0.033 plus 0, or 0.108, an almost 11% chance. Now that we've covered probability and how to use it, let's take a step back and look at what you need to pay attention to in the big picture. In any of the situations that we have talked about, we know that what our counts are counting. In reality, you don't always know that for certain. In the real world, what you could be counting is one of four things: a false or true positive and a false or true negative. This often happens when we're given people or things to test with a positive or negative outcome. Not knowing for certain what your outcome is, these types of situations can have a big influence on your results. Let's take a look at the possibilities in the view of having to take a test on malaria. If you take the test and you test positive, but you don't have malaria, that's a false positive. If you take the test, you test positive, and you do have malaria, then that outcome is a true positive. If you take the test, the outcome is negative, and you do actually have malaria, then you are a false negative. If you take the test, its outcome is negative, and you indeed do not have malaria, then you would be a true negative. You want to know what you are counting so that you can use conditional probability to give you accurate answers. In the case of malaria testing, you might want to know what the probability of having malaria, given that you have a negative test outcome, or a false negative, is. You should be able to see the relationship to our previous discussion on conditional probability. This is very important to understand when trying to diagnose a problem or determine treatment. Just as a note, this type of situation is not limited to human diseases, but could also show up in computers, cars, and all sorts of mechanical devices. In addition to making certain that you know what you are counting, you want to make sure you know what your base rate is. Suppose you were told that the test for malaria is 90% accurate in detecting the presence of malaria. That is, in all of the tests given, 90% return positive for those people who do indeed have malaria. This seems like a shockingly high base rate, and is a great base rate for the test itself. However, the actual rate of malaria present in the human population is only 1%. This is a true base rate, and is what you want when calculating the probability that you actually had malaria. So the base rate for the test, 90%, is not the base rate for the actual number of people walking around with malaria. You want to be very careful when choosing a base rate so you don't end up with the base rate fallacy, where that rate you choose is misleading. The bottom line here, don't get too caught up in calculating probabilities of outcomes until you are certain that you have the correct type of counts and that your base rate actually applies for the outcomes you are looking at. The neat thing about probability is that we can use it to find the chance that we select a specific sample from a population. Recall that a sample is a smaller subset of a population. Let's say we have a population that has 4 members and they had heights of 74, 64, 70, and 64 inches. Further, we want to know the probability we sample 2 individuals from that population that have an average height of less than 65 inches. In this scenario, we have a 1 in 4 chance of selecting one person under 65 inches, and once that person has been sampled, we have a 1 in 3 chance of selecting the other person. This results in an 8.25% chance of selecting a sample size of 2 with an average height of less than 65 inches. These probabilities are easy to calculate when the population is very small. It becomes more difficult as the population grows. In the next module, we will discuss a method for finding the probability of selecting a sample when the population is bigger. And that brings us to the end of Module 3. As always, let me know if you have any questions with the homework or anything else, and I'll respond as quickly as possible, and enjoy the week.